Thank you for coming to today's CITP Lunchtime Seminar. We are very lucky today to have Evan Hepler-Smith. Evan is a PhD candidate in the history department here. He is the 2014-2015 Porter Ogden Jacobus Fellow in the History of Science program here at Princeton, and his research focuses on history of the chemical sciences, scientific data, and information systems. Today, Evan is going to talk to us about AI and the making of a human scientific method. So without further ado, we'll turn it over to you, Evan. Thanks.
Thank you very much, Nick, and my thanks to Joanna and to Laura for setting up this talk today, and to all of you for coming out. This is paclitaxel, Taxol, a significant cancer drug that can be derived from a natural source. The Pacific yew tree, a fairly scarce species. If, like me, you watched a lot of the evening news in the early 1990s, you might have seen this compound come up. You might have seen that it was the object of a race to synthesize this compound. Because if a compound comes from a scarce natural source and it's important to human health, what do? Well, you can synthesize it through an intricate series of chemical manipulations from simple starting materials. But how do you do this, right? How do you come up with such an intricate series of steps that allows you to make such a complex molecule? Well, if you turn to a current standard textbook in organic synthesis, this field, you see that you do so by logical and sensible thinking, not through guesswork, but by thinking backwards. Now, this seems like a fairly obvious thing to do on one level. If you've got a complex molecule that you want to make, you need to somehow work backwards to figure out what you can make it from. But in fact, this method has a history, and its history involves computing. In the 1960s, Harvard chemist E.J. Corey was trying to figure out a way to get computers to help him to plan these syntheses. The computer program that he was putting together, as this textbook describes, was called LASA, and the logic that Corey and his team developed to get computers to help him with this task survives as a method called retrosynthetic analysis, a way of planning syntheses used by almost all organic chemists. This method is so significant that it was one of the primary accomplishments cited in Corey's 1990 Nobel Prize in the development of the methodology of organic chemical synthesis. I, as Nick said, am a graduate student in the program in History of Science here, and for my dissertation, I have been working on how chemicals have been named, a problem that, as it turns out, is not just a narrow question of semantics, linguistics, but a question that engages the history of ideas about representation and classification in the chemical sciences, the political history of the national and international organization of the chemical sciences and industry, and the information technologies that have been used in the chemical sciences and in the chemical industry over the last 125 years. Now, what I'm going to talk to you today kind of comes out of this project, but is part of the next project that I want to move on to in my research, a sort of sweeping project that I'm calling the molecular world. It's going to be a history of the recent history of the sciences, technology, and medicine since the mid-20th century, focalized around two major trends in these fields. First, the emergence of molecular sciences, molecular medicine, molecular biology, material science, nanoscience. And second, the emergence of computational tools and their increasing prominence across many, many different areas of science, technology, and medicine. And it's a story I'm going to tell by looking at the intersections between these two trends, centered on how molecules get onto computers databases and data structures for keeping track of molecules on computers. There are a lot of pieces to this project. Part of it's a history of graph theory, which has interesting connections to chemistry in the late 19th century. Part of it has to do with the role of data structures in chemical regulation. But what I'm going to talk to you about today is how computers matter to science, to the doing of science, to the making of scientific methods. Do you get different kinds of methods and different kinds of knowledge when you employ computational tools for scientific problems? Do you constitute different kinds of objects when you use computers? I think a good case of this is the omes, the genome, the proteome, the culturome, as the text miners at Harvard call the set of all phrases used in a certain language. There are different opinions as to the answer to this question. Some people say, computers don't matter that much. One historian, John Agar, has said that computerization tends to take place in fields where there are existing practices of computation already set, and it doesn't even always take place then. Others say the incorporation of computational methods fundamentally transforms the nature of scientific inquiry, for example, in the biological sciences, the emergence of genomics. These arguments go on, and of course they depend on what kind of enterprise you're looking at. Agar was looking at bureaucracy, at government information management, and Hallam Stevens, the author of a lovely book on the recent history of molecular biology, is looking at genomics. But the story I'm going to tell doesn't give either of those simple answers. And it doesn't in a kind of interesting way. The question of the role of computing in the development of retrosynthetic analysis brings up a couple other questions that I'm going to try to answer for you. First, how did a method developed for use on computers end up taking hold among people instead? As you can see, this statement that the logic survives as a way of planning syntheses used by chemists suggests that the computer programs that it came from kind of didn't survive. Second, retrosynthetic analysis has a peculiar property in that chemists talk about it at once as an incredibly important transformative method, changed the way that synthetic chemistry works. Corey got his Nobel Prize for it. But at the same time, it's also kind of, chemists think, what synthetic chemists had always been doing since the origin of their field. Some form of retrosynthetic analysis, right? Samuel Danishevsky, a leading synthetic organic chemist of the second half of the 20th century. Some form of this method was inherently involved since the very beginning. So I'm going to attack these questions in sort of three parts. First, I'm going to talk about synthesis, give you kind of an overview of what organic chemical synthesis is. Second, I'm going to talk about Corey's project of bringing computers to bear upon it. Third, I'll talk about some of the methods for human chemists that came out of that project. And I'll wrap up a little bit speculatively by talking about what I think is a way of understanding broadly what's going on here, the role of computing in the making of these methods. First, what is synthesis? This is the cover of a 2000 review of the field of organic synthesis. And what I love about this cover is that it's a totally rich, wonderful mess, just crammed with way too much information. And I tend to write my own papers in the same way. So what do we have here? Well, we've got an art and a science. We've got a bunch of little diagrams. We've got a chessboard. We've got some faces. We've got some names. Well, let's start with synthesis. Well, no, actually, let's start with organic chemicals. These compounds here, these diagrams, represent organic chemical compounds. Organic compounds are compounds containing the element carbon, which has the property of bonding to other carbon atoms. That property in a very stable fashion. That property enables nature to create a huge number, from very simple to very complex, of intricately related compounds based on carbon. Synthesis. At the center of the transformation of nature, society, and the human body on a massive scale that the chemical sciences have affected is the synthesis of organic chemical compounds. We're talking about tens of thousands of substances used in a wide array of products. We're all familiar with pharmaceuticals, but synthetic chemicals are in just so many different products, from the chairs that we're sitting in today to the electronics that we're using. These substances are culled from tens of millions of different compounds, both naturally occurring and then predominantly artificial, man-made, that synthetic chemists have created, generating trillions of dollars of annual revenue. The area of synthesis most celebrated by chemists for most of the 20th century is the total synthesis of complex natural products. This is not generally an effort to create a commercially viable process, but rather a means of creating from simple starting materials, as we saw with Taxol before, a complex molecule. It's justified, or has been justified, for most of the 20th century, primarily on the basis of, first, its intrinsic intellectual interest, and second, as basic research that leads to the emergence of broadly applicable new chemical techniques, reagents, and insights about how nature works, how biological processes work. This review and many treatments of synthesis, of total synthesis, go through a series of increasingly impressive accomplishments, from relatively simple molecules like acetic acid, vinegar, and glucose in the 19th century, through incredibly complex synthetic targets that have been successfully synthesized by organic chemists more recently. Like the moves in a chess match, you saw here, or the strokes in an artwork, or episodes in a daring adventure, synthesis is portrayed as a brilliant, artful, skilled achievement of human chemists. And for most of the 20th century, as you can see down here, mostly male chemists. It's like many fields that celebrate kind of individual achievement in this way within the culture of 20th century science and technology. It's a field that has had its troubles, particularly, as you would imagine, in the mid-20th century with its gender dynamics. These names here are names of chemists, but more importantly for the enterprise of total synthesis, they're names of reactions, the moves in this chess game. And this chess game had its Kasparov, its greatest chess master. The mid-20th century Harvard chemist Robert Burns Woodward did a lot to create and embody this culture of total synthesis. He described his syntheses lyrically as adventure. The structure known, he wrote, but not yet accessible to synthesis, is to the chemist what the unclimbed mountain, the uncharted sea, the untilled field, the unreached planet are to other men. He described his syntheses as artful accomplishments, displaying delightful elements of surprise. He wrote, an apparently rather dull grouping of atoms suddenly, under the impact of especially chosen reagents, undergoes unusual transformations which are of great utility in progress toward the objective. The impact on an observer may perhaps be compared with that on a traveler down an uninteresting street who turns through a small doorway into a delightful, charming garden. This is how he's describing his chemical synthesis. Now, Woodward spent most of his career in Harvard's chemistry department. Oh, and this is an example again. Even his students, he kind of wanted to present chemistry as a kind of adventure for them. Men and women who not plan but dare to register in his synthesis course should contact the department administrator. Another synthetic chemist who has spent most of his career at Harvard and who is still there presents a contrasting view of this discipline. This is E.J. Corey, trained at MIT, began his career at the University of Illinois, and joined Woodward at Harvard in 1959. He was cited around 2003. I think the last time anybody did this sort of count is the most cited author in the history of the Journal of the American Chemical Society. And at Harvard, when he arrived, he started teaching a synthesis course. It was called Chemistry 115. It's taken on legendary status for generations of chemists trained at Harvard. And for this course, Corey was looking in the early 60s for a way to present that parade of synthetic accomplishments in a comprehensive and comprehensible way. And the way he did so was he came up with kind of general strategies of synthetic planning that would allow him to sort different classic syntheses together into groups to present them in this course to his students. Soon, during the mid-1960s, he began to recognize and consciously to apply some of the general strategies that he had used as this sorting mechanism in his own research in synthesis. In 1966, he gave a lecture on this approach, advocating the development of general methods for the construction of complex molecules, not relying on intuition and art, but finding a way of understanding synthesis, synthetic planning as a procedure. To be sure, not just a linear procedure, but one that would account for the serendipity that Woodward and others had recognized in synthetic planning through operational loops or cyclic iterative processes. And as the language that he chose suggested, Corey noted that the kind of method making he was looking for bore a vague resemblance to a computer program. And over the following years, Corey pursued this program of general synthetic methodology in the context of building a computer program to help with it. Now, before I get into Corey's program, I want to talk a little bit about another case, maybe a little bit of a better known case to those interested in the history of AI in computational chemistry. In the early 1960s, a geneticist named Joshua Lederberg was at Stanford. And like any good hotshot new Stanford professor, he was interested in things like detecting life in space and doing cool stuff with computers. And he brought these two interests together in a program to put an instrument on a Mars lander that you could send to Mars and that would automatically figure out if there were proteins around on Mars. Now, one way you can figure out if there are proteins around is by putting a sample of a chemical substance into an instrument known as a mass spectrometer. The instrument breaks up a large, complicated molecule into smaller chunks, and those chunks travel towards through an ionized electrical field in such a way that you get peaks representing the mass-to-charge ratio of these chunks. And if you're a very skilled organic chemist who has a lot of experience interpreting these graphs, you can figure out what those chunks were and thus what the original molecule was. It just so happens that the very best chemist at performing this sort of interpretation at that time was at Stanford with Lederberg. And so Lederberg recruited Carl Djerassi to help him with his project of detecting life on Mars through computers. Now, this ended up not coming to much, the Mars life part of it anyway. But what came out of it was a project called Dendral. From Djerassi's point of view, Dendral was going to be a new method for chemists, a new way, much more reliable way than human chemists could develop for interpreting mass spectra, a kind of automated check. He suggested that there should be a computer referee that anytime anybody submitted a structure determination based on mass spec data to a journal, the journal should use the Dendral program to check and make sure that the chemist had done everything correctly. For the other members of the Dendral program, however, chemistry was a sandbox for developing techniques of artificial intelligence. Here we have Bruce Buchanan. He was a philosopher. We have Georgia Sutherland. She was a computer programmer. In the middle, Ed Feigenbaum, a pioneering psychologist and computer scientist working in AI. Joshua Lederberg himself, and Dennis Smith, a computational chemist. So not chemists primarily, but computer scientists, philosophers, AI researchers were the ones driving this program forward. Corey's project was different. What became the LASA program started its life as OCSS, or the Organic Chemistry synthesis simulation program. And that was in 1968, and then a new generation of long hairs came in the next year to the research group. They decided that OCSS apparently sounded too military industrial for their tastes, and they renamed the project the Pacific and Cuddly LASA, Logic and Heuristics Applied to Synthetic Analysis. LASA was a chemical project staffed by chemists, but it employed a distinctive form of chemistry, as I'll describe, and it had chemical dividends. This is to contrast LASA with Dendral, a project in artificial intelligence and directed towards artificial intelligence primarily. I could tell you how it worked, but if the technology cooperates, I will let a member of the LASA group himself do that.
Pictures that you see are being generated on a graphics display terminal by a digital computer. The program which is tractable for synthetic analysis. The version of LASA which will be seen here, which was begun in 1967 at Harvard University. The goal of the project is to develop a tool for use by synthetic organic chemists, which could assist in the planning of organic syntheses. LASA accepts chemical information according to the standard structural diagram conventions familiar to organic chemists. All interaction between the program and the chemist is graphical in nature, using a tablet and stylus device for structural input, and cathode ray tubes for structural display. The general approach to synthetic design used by LASA involves working in what is termed the retrosynthetic direction. That is, in the opposite direction to that in which the synthetic steps are executed in the laboratory. The target molecule, the molecule which the chemist wishes to synthesize, is supplied to the program graphically and processed by LASA. The program then generates a small collection of intermediate structures, each of which is one synthetic step away from the parent structure. Each of these intermediate structures may then be treated by the program as targets and processed further, generating still another level of intermediate structures. If this process is repeated a number of times, eventually a collection of simple structures results, which corresponds to available starting materials. The synthetic pathway produced in this way form a branching structure which is termed the synthesis tree. The nodes of the tree represent synthetic intermediates, and the top or root of the tree represents the target structure.
Okay. So, I can get back to this. Whoop. So, in short, and by the way, that was a member of the LASA group, a grad student named Jeff Howe. That video was made in 1973, I think using special equipment for videotaping CRTs developed at MIT, although I haven't proven that yet. Anyway, so as they described, LASA was an embodiment of the kind of cyclic iterative loops that Corey had described in his 1967 paper. And it did that by separating the procedures of synthetic planning into what Corey and his grad students described as information-centered portions to be carried out by chemists. So a chemist evaluates the structures and makes a decision whether or not to loop back. And logic-centered procedures to be carried out by the computer. The program was built in a modular fashion and was centered on a strategy module. Strategy being the kind of formalized version of those general kind of collections, general classifications Corey had developed for his course, his Chem 115 course of different kinds of syntheses. I can talk a little bit more in Q&A if you'd like about the particular structure of the software system and the hardware that he was using. One of the reasons it's modular was because of the limited storage space on the PDP-1 computer that the team originally used to develop their program. I can also talk about the development of molecular graphics that was referred to in the video. So all of the members of the team, as I've mentioned, were chemists. They were laboratory synthetic chemists. And even the kind of more computational aspects of the program were derived when possible from chemical sources as well. For example, whereas for Dendral, Lederberg was very proud of his graph theoretical algorithm that he had created to generate every possible chemical structure from the ground up, the LASA team simply used the Morgan algorithm, which was a technique developed at Chemical Abstract Service, the main kind of information provider in the American chemical sciences for computer representation of chemical structures. So there was a chemical tool out there, and the LASA team grabbed it in order to integrate their project more completely into the ecosystem of chemical information. So it was a chemical project, but it wasn't just any chemistry. In a paper in the early 1970s, Corey and a couple of his students described that there were a variety of rational schemes for grouping synthetic reactions, that is, reactions that take you from starting materials to a more complex product. But, they wrote, these schemes depend on properties of the reactants, and therefore they're irrelevant to a computer program which analyzes the features of a product. So having information about how reactants react isn't necessarily useful if what you want to do, if the kind of chemical reasoning you want to engage in is how to take a product and unreact it. Because of this, they developed what Corey, in these papers, first termed a retrosynthetic framework. It was a framework that had to be represented separately, differently from synthetic reasoning, using its own vocabulary and its own nomenclature. Otherwise, you would run into intolerable confusion, as it describes. This is a whole new way of chemical thinking that they're developing in the context of trying to figure out how computers can be made to take chemical compounds apart. I'll give you an example. Let's go back to Taxol. If you're thinking retrosynthetically, what you're looking for in Taxol is not the active elements of it, not the parts of it that are likely to react to do chemistry, but the elements of this structure that you can create using chemistry that you know. One of them is right here in the middle. This is a 6-membered ring with 1 double ring. That's the characteristic product of the Diels-Alder reaction, one of the most powerful and generally useful reactions in synthetic organic chemistry. So that, you might think, would be a good place to start. But if you were being especially rigorous in your analysis, you might see, well, there's another 6-membered ring over here. What if there was a way for me to kind of get a double bond into that ring somehow, again, working backwards? Then I could maybe do a Diels-Alder over there. And what the LASA team was up against was trying to find a way of systematically working through every conceivable possibility of this sort. How did they do that? And again, working through possibilities, and this is from a paper in 1974, so that you could work backwards, not just in one direction, but in many. That was the use of the computer. In order to do this, they started by putting together flowcharts. This is a simplified version of one of 11 flowcharts for LASA's Diels-Alder strategy. Again, this is one reaction. We're just looking for ways of backing out using one single reaction out of thousands of different synthetic reactions. They developed 11 of these flowcharts, and they coded them into the program. Now, when they described how they stored these flowcharts, once again, they emphasized that they were doing so not using forms of algorithmic computational reasoning, but as a kind of a way of thinking chemically. They described the language in which they wrote up these flowcharts for the computer, they called Chemtron, as a language based on chemical English, which has been designed to be computer readable and intelligible to a chemist with little or no programming experience. And they insisted no programming was involved in the addition of new search patterns because the Chemtran files were data, they weren't code. That's kind of a semantic difference, but it just goes to show that it was very important to these chemists to present this project to their fellow chemists as something that was a chemical project, not a kind of computational one.
Chemtran flowchart like that? I mean,
Chemtran was a high-level scripting language, yeah. So I mean, it looked like Python or something, but kind of more natural language. The Lhasa group also described dividends, chemical dividends that they got out of this project in the process of making these flowcharts and translating them into Chemtran. They got better general problem-solving ability through making these flowcharts, so they got better at planning syntheses. They discovered interesting and significant new ideas for research. For example, Corey and his first collaborator, a guy named Todd Whipke, described how they had discovered the paramount importance of pairwise relationships between structural features in this process of working backwards. Something, a kind of a conclusion that they only came to through this process of formalizing the analysis of a structure for use in Lhasa. And through making these flowcharts, they got a lot better, as you might imagine, at teaching this stuff to students, improved pedagogical skills. Now, Corey's vision was that teams of chemists at 30 or 40 major universities would start putting together this flowchart, these sorts of flowcharts, encoding the entirety of synthetic organic chemical knowledge in retrosynthetic form. In doing so, Lhasa was going to be a means, or perhaps an occasion, for chemists to construct and practice techniques in the field that Corey had named synthetic methodology. Methods. All the while, Corey kept teaching Chem 115, and as he did so, he incorporated more and more of the vocabulary and notation and methods that had been worked out in the Lhasa project. Now, other chemists, some who had taken this course, wanted to take Corey's really sophisticated but sometimes abstruse methods and language and make it accessible to a broader audience. They started writing textbooks, little pamphlets, teaching courses that simplified the procedures of retrosynthetic analysis. A particularly successful one of these textbooks was Organic Synthesis, written by I think Cambridge or maybe Oxford chemist Stuart Warren in 1982. A book that's intended to teach students to learn the disconnection approach to organic synthesis. In the introduction to this book, Warren writes, before and during these syntheses, planning their syntheses, groups of chemists sitting around blackboards or piles of paper plan the work they are about to undertake. How this planning is done, which the book is going to show you, is the disconnection or synthon approach. Now, Warren doesn't mention Corey, doesn't mention computers once throughout this book. Retrosynthetic analysis in his hands has simply become how chemists do their work. So this shows you, number one, how broadly this method was spreading throughout chemistry, and number two, how Warren succeeded, very successful textbook, in naturalizing this method, making it just how organic chemists worked. Corey wrote his own textbook in 1990, and while he did use the intricate vocabulary and kind of more abstruse methods that he had developed in all of their sophisticated form, he kind of backed off some of his earlier claims about the role of the computer. To be sure, he wrote that the computer, the development of the Lhasa program, along with the use of retrosynthetic analysis in synthetic planning and in the teaching of synthetic planning, had proven the merits and power of his method. And he noted that the development of the computer program demonstrated objectively the validity of the logic that he was teaching, of the method he was teaching in this book. However, the computer program itself had been downgraded from a chemical project to a major challenge, or maybe upgraded to a major challenge in the field of machine intelligence, not in the field of chemistry, one that may someday be met. And indeed, the program that Corey had been developing, the Lhasa project, had continued to be worked on, but had never really caught on. Certainly, there were never groups at 30 or 40 universities busily working away, writing flowcharts for it. And in fact, where the program went, as with so many such projects, was determined by where the money was. So the LASA program kind of spawned significant spin-offs in chemical drawing. The chemical drawing software ChemDraw, used universally throughout the chemical sciences, came out of LASA. And a number of toxicology and pharmacology products in computational chemistry that are developed and used by many pharmaceutical firms and chemical firms came out of this project. And there were similar projects going on with other groups at other universities, most of which went in similar directions. Yeah.
Was it like ethically, morally correct for Stuart Warren not to ever mention Corey? Was Corey relatively core? Was he deliberately slighting him, or did it really become that so that Warren never noticed that he was ignoring?
Well, Warren noticed in 2008 when he published a second edition of his textbook. He wrote, "All that is in this book owes its origin to Corey's work." You could go either way. I think that it is significant that the first textbook that used retrosynthetic analysis that really caught on didn't say anything about computers, which many chemists, especially those who were in a position to be teaching organic chemistry, were super skeptical about. I haven't asked Corey about what he thought about Warren's textbook, but in any case, in the second edition, Warren certainly paid tribute to Corey's influence. He mentioned the LASA program, but again, as we saw at the outset, as something that had been the source of logic that survives not on a computer program, but in a way of planning syntheses used by almost all organic chemists. I'm going to wrap up. So in a way, we're back where we started with an interactive program, LASA. This is a quote from a lecture that Corey gave in 1988. An interactive program that's designed to emulate the techniques of chemists and that is also of great value in developing new and general ways of thinking about synthesis. So this is kind of an exercise in methodological bootstrapping. You stick your methods in to the computer and you somehow get better methods out. Even, again, methods just for chemists working without the help of any machines. Well, this starts to at least answer the question of how retrosynthetic analysis could appear both well-established and transformative. Again, it's this sort of something's going on in which methods that are already used by chemists and become new and general ways of thinking about synthesis that are justified because they're based on methods that were already used by chemists. But still, it would be nice to be able to say something a little bit more specific about what the role is that the computer is playing in this method-making process. And to do so, we're going to go back to Woodward. In 1976, Woodward, never the most generous of colleagues, reputedly, nevertheless decided to nominate his colleague E.J. Corey for the National Medal of Science. In this nomination, he wrote that by means of the explicit formulation of strategies and problem-solving methods for organic synthesis, Corey had contributed to a major change in thinking about synthetic problems. There's something important about Corey's explicitness for Woodward. And this got me thinking about explication as a mode in which we can talk about the function of the computer in this process of method making. By explication, what I mean is the presentation of a new description of something, in this case, the practices of synthetic design, how you plan an organic chemical synthesis. The presentation of this thing in a manner that declares the contents of this new description to have been present all along, waiting to be unfolded. I use the term explication to draw in part upon the term's use in analytic philosophy. The idea that what you do is you take a statement and you unpack its hidden logical structure, that's a sort of a worthy enterprise. But also in literary studies coming out of the French critical approach of the Explication du texte and its adoption and democratization among the American new critics in the early to mid 20th century, critics who, working with an enormous population of not necessarily super educated new students, many coming in off of the GI Bill, developed a method of literary critique in which all you needed was the text in front of you, and that a new aesthetic whole could be realized simply through carefully picking apart what was already in the text and reassembling it in some way. You see the same sort of discussions of explicitness or explication and computers side by side in a few different fields during this period of the late 60s and early 70s. For instance, Jonathan Culler, the literary critic in Structuralist Poetics, describes structuralist studies of language and literature as adequate only if they are sufficiently explicit for different linguists to use the apparatus of a given theory to reach the same results, or more precisely, for a computer to be programmed to do so. Princeton's own T.S. Kuhn, in Second Thoughts on Paradigms, a follow-up to his famous Structure of Scientific Revolutions, writes that the explication of the term paradigm and the scientific community that it represents can be achieved through modeling on a computer. Indeed, he at least claimed to have been working on a computer program to figure out how scientific communities are realized, how they form. The computers in both of these cases aren't necessarily real. It's hard to tell whether anybody, I mean, it doesn't seem like Culler was actually using a computer, and Kuhn might have been, who knows. But they're kind of thought technologies at the very least to aid in this process of explication. Explication with the goal of making a method of clarifying a concept. I'm going to conclude with one more reference to adventure that I think encapsulates this view of what Corey was up to, what he did with the computer in making the method of retrosynthetic analysis. It's not an allusion to adventure in Woodward's kind of imperialist sense of armies marching off to conquer the next synthetic target and tame the plains of hitherto unconquered chemical realms, but rather a passage from the work of Joseph Campbell, the American myth scholar of myth. Campbell writes of the journey of the hero into the other world and back again. That the two worlds, the divine and the human, can be pictured only as distinct from each other. Different as life and death, as day and night, as human and machine, perhaps. The hero adventures out of the land we know into darkness. There he accomplishes his adventure, or is again simply lost to us, imprisoned or in danger. And his return is described as a coming back out of that yonder zone. Nevertheless, and here is a great key to the understanding of myth and symbol, the two kingdoms, human and computer, in our case, perhaps, are actually one. The realm of the gods is a forgotten dimension of the world we know. Thank you.